Section 39 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in July 2015. The Science History of the Universe, Volume 1. Edited by Francis Roald Wheeler. Astronomy. Chapter 25, Part 2. Cosmogony and Stellar Evolution. At the very end of the 19th century, F.R. Moulton and T.C. Chamberlin of the University of Chicago denied some of the fundamental ideas involved in the nebula hypothesis. Not only was their work destructive in that they advanced phenomena which the theory of Laplace could not explain, but which were in fact controverted directly by observation, but they constructed a cosmical theory in which these elements were taken into consideration, and in which, in large part, the conditions were met. The chief objections to the theory of Laplace, as stated by Professor Moulton, are as follows. 1. The considerable mutual inclinations of the planes of the planetary orbits and the inclination of the plane of the Sun's equator to the general plane of the system are not to be expected on the basis of the ring theory. 2. The eccentricities of the planetary orbits are not to be expected on the basis of the ring theory. 3. The orbits of the planetoids contradict the ring theory. 4. The rapid revolution of Phobos and of the particles of the inner ring of Saturn cannot be satisfactorily explained. 5. The presence of light elements in the Earth is not to be expected. 6. A series of rings could not have been left off. 7. A ring could not have been condensed into a planet. 8. The moment of momentum of the present system is less than 1/200th of that of the supposed initial nebula. 9. The retrograde revolutions of the 9th satellite of Saturn and, probably, of the 7th satellite of Jupiter flatly contradict the theory. Of these objections, one of the most important is the question of the leaving off of the rings at certain intervals during the contraction of the nebulae. On this point, Professor Moulton writes in his Introduction to Astronomy, "It is easy to overlook the fact that the postulated nebula must have been excessively rare. According to the hypothesis made, it must have been denser at its center than near its periphery. But if we suppose that it was homogeneous and that it reached out to Neptune's orbit, we find that its density was only 1/250,000,000 that of air at the sea level. Neptune's ring could not have been so dense as this, which is many times rarer than the best vacuum yet produced in our laboratories. Now, a ring of such rarity would have had no cohesion and would not have separated except particle by particle. When the process was once started, it seems that it should have been continuous instead of intermittent as the theory supposes. The theory postulates that when a ring was left behind, the nebula was made stable for a long period of contraction. Roche has attempted to show that rings of considerable dimensions would be abandoned at certain intervals, but his work on this point is far from conclusive. Every other writer on the subject has keenly felt this difficulty. Thus, Faye, in his modification of the Laplacian theory, supposed that the whole nebula broke up into rings simultaneously. "We may assume, for the sake of argument," he says, "that rings are abandoned and inquire whether they will unite into planets or not. The matter of the ring would be very widely spread out, and mutual gravitation of its parts would be very feeble. The appropriate investigation shows that the tidal forces coming from the interior mass would more strongly tend to scatter the material than its gravitation would to gather it together into a plane. Consequently, a ring could not even start to condense into a planet. It would be something like a comet which becomes utterly dissipated by tidal forces. To give every possible advantage to the ring theory, we may assume that all the matter has been gathered into a planet except a ring of very small particles, and then ask ourselves whether this minute remainder will be brought to the planet. Investigation shows a strong probability that only that part of the ring which is within 60 degrees of the planet could be brought onto it in any time, however long. That is, if we assume that the process of formation of a planet out of a ring is almost finished, we find that it cannot complete itself. This shows the strong improbability that the assumed stage could ever have been reached by condensation from a more uniform ring. Then it must be considered that the 9th satellite of Saturn and the 7th satellite of Jupiter revolve in a direction contrary to the other revolutions and rotations of the solar system, which would be an impossibility if the Laplacian doctrine were true. Finally, notwithstanding a careful and thorough study of nebulae developed by photography to a point of great refinement, there has been found no trace of a nebula which is in the course of breaking up into concentric rings. The spiral nebulae, such as the theory propounded by Professors Chamberlain and Moulton required, are of the normal type of nebulae, and it is this fact, brought out in the brilliant discoveries of Professor Keeler, that has largely produced the new theory which has been termed by its originators the planetesimal theory. This planetesimal hypothesis today is attracting widespread and favorable attention from many astronomers and geologists. While it explains the formation of the solar system and other systems, it does not eliminate the question of primitive matter, which doubtless must have been nebulous. While spiral nebulae may have been formed by the collision or interaction of large suns, yet these in turn demand for their origin a similar occurrence, so that one is led rather strongly to the belief that the formation of systems of suns and worlds may be a continuous process. The planetesimal hypothesis has been summarized in the following simple statement by Professor James F. Kemp in the course of a lecture in which its application to the origin and development of the world is discussed. He writes: Instead of a highly heated and subsequently cooled and solidified gaseous original, minute particles of matter, which may have been molecules, are believed to have moved in orbits around a common center in a manner analogous to the solar system of today. In their evolution they became aggregated into larger bodies, such as the planets and the Earth, continuing in groups the motions and relations which they possessed when individuals. As the mass gradually increased, the pressure of the outer layers consolidated the core, and by the mechanical changes involved, produced those internal stores of heat with which we are familiar in volcanoes and in deep borings and mines. Vapors or liquids in the original cold particles are believed to have been gradually squeezed out by this pressure. The little particles are called planetesimals or diminutive planets. Like all attempts to formulate primeval conditions, the data of this new conception are partly matters of observation, partly assumptions. Speculation enters in a very large degree, and, as in the case of various and widely differing estimates of the age of the Earth based on assumed rates of cooling, once the data were provided, mathematical reasoning goes to a conclusion with unerring accuracy. But the correctness of the solution turns on the reliability of the original data, and where these are so largely assumptive, the conclusions are from time to time subject to change. Yet we must have a starting point, and the striking contrasts of the older and later views cannot but impress everyone who reflects upon them. The former postulates a highly heated original, the latter a cold one. The one begins with gaseous matter, the other with solid. The one draws upon an original but diminishing store of heat, the other develops heat continuously by mechanical processes. In many ways the two are diametrically opposed, yet some have raised the question whether, in order to obtain a swarm of separate cold particles, we must not in our thought go still farther back to a gaseous or nebulous score, and it is not clear that we have yet escaped the necessity of at least the essential features of the nebular hypothesis. Whatever theory is studied or adopted, it is clear that the building of suns and the building of worlds is a process of evolution in which the original matter must undergo transformation. The process may be continuous and may extend through infinite time. The collision of suns may have produced nebulae, and these nebulae in turn may gradually develop themselves into suns again. It seems reasonably certain that nebulae are the stuff from which the stars are made. Of the many types of nebulae, the spiral forms are considered the more primitive. There is indeed evidence to show that even such apparently irregular nebulae as that in Orion still preserve traces of original spiral formation. Professor Dewar has experimentally proved that, at the low temperature prevailing in the outer regions of a nebula, it is one of the properties of a dust particle to attract and condense on its surface whatever gas may be within its immediate vicinity. It may be safely assumed, therefore, that each particle of dust hurled out by the explosion of two colliding suns bears its charge of gas. That these gas-laden dust particles should collide with one another would follow from their motion and their excessive number, and that these particles should be cemented together by the film of liquid gases on their surfaces would in turn follow from the fact of their collision. Thus, in the course of centuries, large grains or aggregations of matter constituting meteorites are formed, which, by gravitational attraction, gather about them part of the remaining dust and gas. Stars, comets, and meteorites from other systems will also wander into the nebula, attracting the gas and dust of the nebula. Evidence of this straining of a nebula by an immigrant star is to be found in many a constellation, notably in the Swan, where a distinct lane has been plowed through a nebula by an errant star. By this upbuilding of meteorites from colliding gas-laden dust particles and the concentration of nebular matter by bodies which have strayed into the nebula, the entire mass of gas and dust is converted in the lapse of ages into clusters of stars, slowly revolving about the central sun in periods of thousands of years. Such star clusters are familiar objects in the heavens. They may be found in the Pleiades, in Pegasus, and in other constellations. Each star in a cluster may be regarded as either the center of a new solar system or as a newborn world, not a rock-bound, sea-swept world as yet, such as the Earth, but a glowing chaotic mass, an embryo which will cool and shrink as it cools, and which will eventually chill into a solid sphere. The central sun, because of its greater size, will blaze on for centuries after the clusters about it have congealed into planets. Because the shrinking and cooling are not of a year's nor even of a century's duration, but are extended over millions of years, it is possible to study the various stages of the process in stars that have been formed from nebulae at widely different epochs. The method of investigation bears some relation to the system devised by the evolutionists in tracing the development of life on this earth. With the aid of fossils dug out of the earth, the paleontologist has ingeniously bound the living present to the dead past with the chain of evolution, and shown very convincingly how the creatures that now roam the earth are inevitably linked with the extinct animals of prehistoric time. An analogous system of stellar classification, formulated by Professor W. W. Campbell, throws not a little light on the ancestry of the myriad of stars whose rays pierce the heavens. Such a search indubitably points to nebulae as the stuff of which worlds are fashioned. In estimating the period which probably elapses before a star in a cluster will shrink into an encrusted world, the color of the star's light plays no small part. Red-hot iron is not nearly so hot as white-hot iron. The color of the molten metal gives the iron founder a clue to its temperature. Similarly, a star's temperature may be gauged by its tint. Since temperature, and therefore color, alter with age, it is possible to state in a rough way that red stars are the oldest of luminous bodies, and that the orange, yellow, and white stars follow in respective antiquity. Youngest and hottest of all are the bluish-white stars. The spectroscope draws nicer distinctions than those which can be drawn by color alone. Professor Campbell has discovered from his study of stellar spectra that when the spectrum of a star is rich in the bright lines of the gases hydrogen and helium, it is certain that the star in question is young. Indeed, the presence of nebulous masses about many stars in this stage of their evolution proves how true is Professor Campbell's conception. In the constellation of Orion, for example, is a nebula in which stars are plunged. The spectra of the nebula and of the stars exhibit the same lines. Can there be any doubt that the stars were formed from the nebula? In passing from the white stage of infancy, the star shrinks more and more. The result is a change in the spectrum. The metals calcium and iron appear in their characteristic lines. Vega and Sirius are stars of this type. As the star ages, the hydrogen lines thin out and the lines of the metals become stronger and more numerous. When a stage is reached corresponding with that of our own Sun, a yellow stage, which may be considered the very summit of stellar life, some 20,000 metallic lines appear. Then comes a gradual cooling. As it changes in hue from yellow to red, more complex chemical combinations are found in the star, and carbon makes its appearance. Then follows a stage represented by the planet Jupiter, still gaseous, still hot, but no longer markedly luminous without the aid of the Sun's borrowed light. A further step brings with it external solidification, the formation of a crust enclosing a hot interior, at which point the Earth has arrived. The last and most pathetic period is represented by the Moon, frozen, desolate, dead. End of section 39. End of The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler.